Okay. Thank you, and thanks a lot for the invitation. I'm very happy to be back in Tübingen finally after so many years. So after you've heard so much about continuous optimization and convex, non-convex, I would like to sort of complete the optimization sessions with talking about discrete optimization. And since discrete optimization is a very large field, I'm going to talk to you a little bit about a special topic that's particularly useful for machine learning, and that is the topic of submodularity and set functions. So what is submodularity? What are set functions? Let's try to start very simply. What is a set function? So in all the settings that we have here, we will have what is called a ground set of items. So it's just a collection of items that you can choose from. For example, different items you may want to have for lunch. And we're going to select subsets of these items, and then we have a function, that's the set function, that takes subsets of these items and gives us a score for these. So the score could mean a cost, what does it cost to buy these items together, or it could be the utility, how valuable are these items to you, or it could be something like a probability, how likely is it that if these items are actually, say, locations, to observe objects in these locations and so on. So these are set functions. So whenever I write this capital F, that means we have a set function, and this V always means we have this ground set of items that we choose. So obviously that looks already like a pretty realistic setup, but it doesn't look so related to machine learning. So let's sort of complete my title, and let's see where in machine learning do set functions and subset selection problems come up. So basically what we have is we have this machine learning pipeline that we have training data, and we learn a model from this, and then we make predictions on various types of items. So where in this pipeline do subset selections arise? And essentially everywhere. So just sort of to show you some examples as a motivation, let's look at training data. And essentially there's two basic setups where subset selection problems arise. One is if we have too much data, and one is if we have too little data. So where do we have too much data? Think of if your data, I say, is coming from a camera that's, say, monitoring a highway or monitoring some whatever, national park or something. So constantly you get this big video stream of data, so you have all these different frames. Maybe all these frames are not enough to actually send them somewhere to a server, to process them there, to learn from them, to learn from that data. So what you have to do is actually to compress it, to maybe just select a subset of these frames that you can learn from, as well as you had the entire stream. So this is essentially the problem of how do I summarize my data. If I have a very large data set, can I sort of select a few of these data points, not too many, that I can process them faster and learn from them, as well as if I had seen the entire data set. So basically select the representative subset, and in that case, what would our scoring function be? How would you select those? So essentially the scoring function in this case would measure something like information. How much information about the entire data is in the subset that I have selected. So this is the other setting. What if I have too little data? What if every data point means that I have to run an experiment to take a measurement? So actually it's very expensive to have data. Maybe I have to ask a human to label it or so. Now I have to be smart about, again, which data points do I want to have? Which data point give me as much information as possible about the learning problem that I have, because it's expensive to collect them. So it's essentially the same problem, just a little bit of a different setup. So this happens if you, say, have to place sensors, if you have to design experiments in biology or chemistry, if you have to ask users for labels and so on. In both cases, the scoring function that we would have is something like how valuable is this subset of data or measurements for the learning problem I have? How much information do I get from this? Okay, so much about training data. What about the actual model learning itself? And there also subset selection problems can come up. Let me just show you one example here. So this is the example of sparsity. So let's say we have very high dimensional data. For example, our data vector is actually the DNA or the measurements of the gene expressions of an entire chromosome or something. So that's a very high dimensional vector. And let's say we want to predict from these expressions the association with a certain disease. Does the person have the disease or not? And what we actually know is that probably not the entire genome is predicted for this, but a small subset is actually enough. So here what we want is our subset selection here is which of these coordinates, which parts of the genome are actually the ones that we are looking after, that are associated with this. So in this case, the subset selection is coordinate selection or variable selection. So essentially, if we have, say, a classifier or regression problem, we want our classifier to use only a few of the coordinates. So this is sparsity either in the actual data or in the W's. And then we could also have something like we know something more other than just sparsity. Maybe we say that certain structures of patterns are more likely than others. Maybe this thing is read out in a sequence, so you know that the important ones or the relevant ones are sort of consecutively one after the other instead of just arbitrarily spread. So sort of consecutive small sequences are better than spread out. So 10 sort of one next to each other is better than 10 spread out across the genome. So this is the case of coherence. So now we need a scoring function that sort of tells us, okay, this is my prior assumptions on what the sparsity pattern looks like. And similarly, we can use this to select edges in graphs and learn networks, things like that. So this is about the learning part. So here we actually have the subset selection within the learning part. There's other parts in learning models where subset selections come up. Think about having a large neural network that you have trained and you want to compress it. Because maybe you want to fit it into a cell phone or so. So at the end of the day, maybe you want to select just a few of the neurons, not all of them, throw away some of them, but retain the information that you have of the model that you have learned. Or maybe you're dealing with very large matrices. So you think you will talk about kernel methods tomorrow or day after. So in these methods, the central object is this big kernel matrix that you have. So this is very convenient in certain ways. It's very bulky in other ways, because if you have very large data, it's going to be a very large matrix. And it's maybe very expensive to deal with it. So what do? We try to do a low-rank approximation. And one way to do this is what's called the Nystrom approximation. Yeah. Okay, thanks. I'll need this later on. Yeah. Anyways, so what's the Nystrom approximation? Essentially, you take your big matrix, you select a few columns of this matrix, and just from these columns, you can do a reconstruction, a sparse approximation. So you put these columns together, take this very tall matrix times its transpose, and then in the middle, you do a little reweighting, a small inverse. So there, the subset selection is which of the columns do you select? Which of the parts of your model do you retain to approximate the full model? So that's, again, a subset selection. So last but not least, even the prediction problem itself can involve subsets in subset selection. Think about an example like this. So this is a news website. So there's essentially lots of news that are coming up every day. And we want to summarize this news for a user. So what we may have learned is something like a preference function for the user. This user is interested in certain topics, but not others. But at the end of the day, we cannot show all the news to the user. We have to select a few of them and display them on the web page because there's limited space. So which ones of these do we choose? Essentially, again, it's just a subset selection problem where the ground set here is the set of all news. So in this case, our scoring function would measure something like how relevant is this subset of news to this user, and also how much well does it represent the entirety of the news of this day. So if we missed any important information, is everything covered at least to some extent? And this diversity comes up because we don't want to be too redundant. We don't have a lot of space, so we don't want to be redundant. So essentially, we will end up selecting news that are somehow diverse, different from each other. Similar things happen if you think about web search, returning answers to queries of a user. And so essentially, throughout, in different ways, subset selection problems come up in machine learning. So how do we address these? How do we solve? So first of all, is there something that they have in common? And of course, we already sort of hinted at that. Essentially, you can formulate all of these different problems is find a subset of items, where items can mean different things, that minimizes or maximizes some set function f of s, minimizes a cost, or maximizes some kind of utility or score. So if we basically can solve this optimization problem, then we can solve all of these problems. The f of s is different in the different settings, and I haven't really formally said what it is, but sort of intuitively. So that's good news, sort of we have a common framework. But at the same time, it's not yet good news because this problem as it is can be very, very hard computationally. So in the worst case, you would actually have to search through all different subsets to figure out which one is the best one without any further assumptions. And that can become really, really tedious. So if you think about just 100 items, in many of these cases, we have many more than 100 items to choose from. We have 2 to the 100 possibilities of choosing. So how much is 2 to the 100? It looks big. It's actually very big. So here's one illustration how big it is. You take a sheet of paper. It's like 0.5 millimeters thick. You fold it. It's doubling. So you fold it 100 times. How thick does it become? It becomes actually much, much thicker than going to the moon and back. So it becomes like 13.4 billion light years. So if you think this is like the number of, equivalent to the number of sets you'd have to search. If now each set maybe takes a few a fraction of a millisecond even, still it's going to take you lots and lots of years to. So that's just not feasible. So what we want is, we want some more assumptions, some structure in there that lets us reduce the running time from, say, these billion light years to about 10 centimeters. So what is this property? What can we use that's realistic enough that it holds for many of these settings and that's also computationally feasible? And one such structure I'll talk about today is that of submodularity. So that's why we are interested in it. So what are we going to talk about today? Here's my roadmap. So first, what is submodularity? So I've given you some motivation why we may care about it. Where does it come up and why is it useful? Mostly I talk about optimization. So how can we optimize submodular functions? How is the structure of submodularity useful? And then I'll show you, as time permits, some further connections and directions of sort of more current research. Okay, so let's start with what actually does submodularity mean? What is a submodular set function? And let's look at this as an example. So let's take the sensor selection problem. So here, this is like the data subset selection problem, selecting your measurements. So you have all possible locations in a room. You want to place a few sensors to collect measurements at these sensors to basically monitor the temperature in all places in this room, to detect fire outbreaks or something. So here, ground set is all possible locations, and our set function is something like information. So what is the one property that this satisfies? And here it is. So here's the quantity we care about. The quantity we care about here will be called the marginal gain. The marginal gain simply means if I have selected a few items, let's say locations 1 and 2, and I've placed a sensor there, how much does my function increase if I add one more sensor? That's the marginal gain of the sensors. Basically, the gain that I get from adding this particular thing to the subset that I currently. So it's a function of two things, the subset A, which is the blue part, and the new sensor, which is the red. So what happens to this marginal gain? So now let's see what does this how does this marginal gain behave. So now what we'll do is we'll compare the marginal gain as we place more and more sensors. So let's say we have a setting we started out, we place 2 of them, and we get the marginal gain of that one sensor. How much more information could we get by placing this measurement? And probably a lot, because it sort of covers some of the area that we haven't observed. But now what happens if we have selected already much more? So on the right-hand side, I have a superset, meaning I've added some more sensors. So now what happens to the marginal gain of exactly the same guy? I'm placing it in the middle, and now I'm already sort of have measured most of the area that this guy actually covers. So in this case, my marginal gain on the right-hand side is much smaller than on the left. I already know everything. One more item of information doesn't gain me as much as if I know. So this is essentially the principle of submodularity, is that of diminishing marginal gain. The idea is very simple and intuitive. The larger my set A becomes, the smaller is the marginal gain of any item that I'm adding to. So I'm always looking at the same item to add, and as my set grows, my marginal gains can always shrink. They can never increase. The more I know, the less I gain from any additional information. So this is the central inequality. It means diminishing marginal gains, diminishing returns, and this is submodularity. This is the one inequality that you should remember. So submodularity can come up obviously in utility functions like information, like coverage, can come up in cost functions as well. So what does it look like in cost functions? So let's say here the subset of items that we select, again, is our food items, and I'm adding a drink to a meal that I bought. So in some cases, this may be, well, the additional cost that I have to pay for adding this drink is just the cost of the drink. But maybe I get a free refill. So after I have bought this drink, all the other drinks of the same kind come from. So here, the marginal cost in this case is smaller the more I buy. It's sort of also the intuition that the more I buy on average, each item costs less. So you see this as like buy one, get one free or free refills. Essentially, it's the economies of scale. And this is why submodular functions also come up a lot in economics to model exactly this phenomenon. The more I buy, the more I produce, the less expensive. So it's the same inequality. Okay, so there's one more definition I would like to show you. This is just the same that we have seen, diminishing marginal gains, diminishing costs. And there's an equivalent way to write this condition. And sometimes one is more intuitive. I think this one is the more intuitive one, but sometimes one is more convenient to prove submodularity than the other one. So what's the other one? The other one has to do with unions and intersections. So now we take any two arbitrary sets, versus here they have to be sets of each other. And we just look at, we evaluate f at s and t independently, and then we look at it at the intersection and the union. And the f of s plus f of t always has to be bigger or equal than the union and the intersection. And how are these two related? I'm not going to prove it formally for you, but essentially you have to do pattern matching and a little bit more of that. So basically pattern matching means match the red ones and the blue ones, rearrange a little bit, and you see that S union T is going to be B and E. That's basically the union of everything that we're looking at. And S intersect T in this case. And then you just can see that essentially from that. So just to remember, let me just write down the inequalities here. So one, we have if A is a subset of B, we want f of A and E. So I kind of omit the curly braces here, that it looks a little less messy. Or we have the one. Yeah, it's just the same inequality. Okay, this is just the same inequality that you can sort of look at it again as equal on. Just the same. All right, so now we know the definition. Let's look at some examples of submodular functions. Where do they come up? And here's one example. That's one simple way of modeling the sensor selection problem that we saw in Tübingen. So here, my ground set of items is all possible locations. And the gain that I'm getting, my utility function, is the area that's jointly covered by these sensors. And each sensor is modeled as a disk, just a disk around the location that I select. So now my submodular function is just the area that's going to stand by them. So now if I look at the marginal gain, if I've selected a few and I'm adding the green one, I'm getting a lot. As I have selected more and more, essentially the additional area that I'm covering gets smaller and smaller and smaller. Right? So proof by picture, coverage is a submodular function, just the jointly covered strip. So now, of course, if you think about the sensor selection problem, this is a very crude model of doing like information and sensor selection. It's already very useful, but it's kind of also very, could we do a little bit more sophisticated? So here's another example of modeling the sensor placement problem with a graphical model. So here, what this picture shows is what we're looking at, what we're interested in is some unknown temperatures. So these are these phi variables here. And these temperatures have dependencies. Basically, this means if I two temperatures at close by locations are positively correlated. If I know something about one, I kind of know something about the other one as well, because I assume them to be somehow close. So this is kind of the information about the structure that I have, about the structure of the temperatures. And now the actual measurements that I can take is not the real temperatures, but it's the real temperature in these locations plus some noise. So these are the x variables. The x is just y plus noise. And now I have to select which of these x's do I want to observe. What's the measurements I want to make to learn as much as possible about all of the y variables, which I can never observe directly. And how would I model this, like mathematically? Essentially, the way we model this is just by using information functions. What I'm going to do is, as my utility, I'm going to look at, okay, first, what is the uncertainty about my unknown random variables here, the y's, if I don't observe anything? And how much does this uncertainty shrink if I observe in location Z? And I want to maximize this shrink. So I want to basically, I essentially want to shrink it to 0, ideally. So how much does my uncertainty shrink if I select sensors in location A? And this is also called the mutual information between what I have selected as my observations and the unknown bytes. So mutual information in this setting, and in fact also discrete entropy, is a submodular. So this is a more realistic model, and it also satisfies submodularity. So here's sort of a little thing to work out for yourself. This thing, why mutual information is actually submodular in this setting, relies on the fact that discrete entropy is a submodular function. So just the function that measures uncertainty of random variables, actually. So this is the H, the discrete entropy. So if you have a set of discrete random variables, you pick a subset S of these, you measure their entropy, that's going to be a submodular function. So now, as a little exercise, and I'll put sort of the solution in the slide, you can work out what does it actually mean to have diminishing marginal gains with discrete entropy. What does the marginal gain actually mean in case of the entropy? So we've seen now a few information theoretic functions. Let's look at some other examples where submodularity. And one other area where submodularity is applied and very popular is that of summarization and recommendation. So if you think about the news, if you think about summarizing video sequences, essentially what you want is you want to capture the content. So you want something that somehow has essentially coverage of content, or something like diversity, non-redundancy of the subsets that you're selecting. Similarly, if you think about recommendation, maybe you want to recommend something if the user has bought these items, something that's somehow relevant to the user, but at the same time, if the user is currently buying a cell phone, it's very unlikely that he's going to buy another cell phone the same shopping day. So maybe recommending another cell phone to sort of add to the purchase is not a good thing. Maybe you want to have some diversity in the items that you recommend. So what we want in these applications, typically something like modeling relevance and coverage, modeling diversity, and maybe personalizing per user, which essentially means learning these functions and adapting them to features. I'm going to say something a little bit about learning in the end, and let's look at what kinds of functions would model diversity and coverage. So here is one simple example how you could model this. So see, here all the black dots are the items that I have, and the red dots are the items that I have selected. And now essentially I just look at, is every item in my set well represented? So what this means, for every item in my set, I'm essentially looking what's the closest representative points that I have selected and how similar are they. The closer that I have a representative point, the higher is the similarity score that I'm getting. And you also see the diminishing returns. If I have one close by representative point, having another close by point doesn't really help me much because I'm only selecting the best. And now I just do this summing up over all of these black dots, and I want essentially all of them to be represented then my function. That's one way, and essentially ensures that you're sort of capturing the content of this data set. Another way to do this is to say, well, my black dots are actually clustered, for example, in topics or something like that, and I want to capture all of these topics. So essentially what I'll do is I'll try to enforce that I'm going to pick at least one guy from each topic. And the way you can enforce that or encourage that is to say, well, for the first guy I pick in the topic, I get a score of 1. For the second guy I pick in the topic, I get maybe a score of a half. For the third guy, a third, and so on. So basically, you get diminishing returns for picking guys from the same topic. So what you essentially do is you count the guys in each topic, and then you use some concave function count those. So that will encourage to sort of cover all your topics. So these are two examples how you can model these relevance functions, and then you can essentially learn what's a good combination of these, what are the parameters of these that fit a use. Let me show you one more example, and this is a somewhat different example, but it's also a very important example of a submodular function, and this is graph cut. So maybe you know what is a graph cut function. Essentially, think you have a network, and you're selecting a subset of nodes in this network. And now your scoring function, or your cost function in this case, means if you take the set of nodes and you look at all the edges that go between your set and all the other nodes outside of your set, count the number of edges. This is basically the edges you would have to cut through if you would cut out this set of nodes from your graph. You can use this, for example, for clustering, because if you minimize it, you would essentially find well-separated groups of nodes. It's used in many different systems. So this is a cut function. Just count all the edges that go between your set and the rest. So why is this a submodular? And to prove this, let's look at the smallest possible interesting graph, and this is the graph of two. So in this case, what we will show is not diminishing returns, but we'll use the other inequality, which means f of s plus f of t is bigger than f of s union t plus f of s intersect. And since we really have only 2 items, so our ground set is very small, there's only one interesting case of this inequality, and this is if s is u and if t is v. And then the union of these is basically both, and the intersection is none of them. So this is the only inequality we really have to look at. So what does this mean? What does it actually become? What is f of u? So now we pick u and we don't pick v, so there's basically one edge in between that we're cutting. So we have to pay the weight of this edge. That means the cost that we have is the weight of the edge. Similarly, if we pick the other node, we again are cutting the edge. So now what happens if we pick both of them? There's no more edge that we are cutting, because there's really only that one edge. And if we pick nothing, by definition, we're also not cutting it. So now, what does it mean? We have on the left-hand side the weight, twice the weight between these edges, and then we have 0 and 0. If the edge weight is positive, it's going to hold. Left-hand side is bigger than right. So submodularity. And now, why does it hold for the entire graph? Essentially, you can write the entire graph cut function as just the sum of these edgewise cuts. And a sum, if you take a sum of submodular functions, this is also going to be submodular. Essentially, you're just sort of summing up these inequalities, still going to hold. So the cut function of the entire graph also is cut. So now we already have a good collection of different submodular functions that come up in different applications. So let me just show you like a little outline of some examples that we've looked at and some other examples. So we looked at mutual information and entropy. Often submodular functions arise when you talk about rank. So if you take a set of vectors and you put them together in a matrix and you look what is the rank of this matrix, that's also going to be a submodular function. And this actually, just like actually entropy, it has to do with dependence. One has to do with linear dependence, one has to do with statistical dependence, but essentially it's not so far. And then there's also combinatorial types of ranks that you can model with them, and so on. Then there's coverage functions. And randomized versions of coverage functions come up, for example, if you look at spread of information in social networks. So if what you're selecting is actually seed nodes in a network, and from these seed nodes, you start a cascade of information spreading through this network, and then you measure after t time steps how many people have you reached in the network in expectation. That's going to be a submodular function. So if you want to maximize influence in a social network, it's most likely some kind of submodular maximization. And there's graph cuts, and there's several others. Okay, so we have a few examples. Let me say a few words about sort of the history of submodularity and generally like where does it come. So here I just show 4 people who worked sort of on some of the foundations of submodularity, some of the polyhedral foundations, and if you see where did actually some of the submodularity come up in the first place, it was in combinatorial optimization, for example. Jack Edmonds wrote a paper on certain polyhedra and matroids or some combinatorial concepts. In game theory, as utility functions of games, of cooperative games, and relations to convexity and so on. So this was around, Choquet was in 55, and these other guys around early 70s, 80s. This is when these papers were written. So where else do submodular functions come up? Essentially in many, many different places. So I mentioned game theory. There's matroid theory, which is essentially parts of combinatorics. There's stochastic processes. I'm going to talk a little bit about probability distributions and set functions in the end. There's graph theory, so cut functions. There's many other things that are related in graph theory to submodularity. There's information theory and also electrical networks theory related to submodularity. So it comes up in many different places and also in machine learning. So we'll look at how useful is it for machine. Okay, so why do we care about submodularity so much? And to sort of motivate this a bit more, let me show you one quote from a paper from Laszlo Lovász. And what he was doing is he was first thinking about, well, why are convex functions so important in optimization? So this was in 83, but this essentially still holds. Why have they played such a big role? Essentially, he mentioned a few points. One was they occur in many different places. And often, like if you look at these different applications, that's the only unifying non-trivial property that holds for all of these applications. So it's very frequent. The second thing is you can do modifications. So your functions, there's many different modifications you can do in convexity still holds. And the third thing was that's maybe also very important one is they're still, they're rich enough to model many things, and they're also rich enough to actually allow some interesting theory. For example, you can have efficient minimization for convex, which you in general don't have for all functions. So you have seen this in some of the research. So, and then he says, why? Well, what is their analogon in discrete optimization? He says, well, it is less apparent, but we claim and hope to prove to a certain extent that a similar role is played in discrete optimization by submodular set functions. So he draws the analogy between submodularity and convexity and says many of these properties actually also hold for submodular functions. So this is an interesting statement. But if you think about it, and if you think about actually this definition of diminishing returns, there's an interesting question that arises. If you think about diminishing returns, the marginal gain is actually like a discrete derivative. So what this would mean is sort of you have diminishing discrete derivatives. But which functions have diminishing derivatives? It's actually concave functions. If you think about it, like derivatives become smaller and smaller and smaller. But he says, no, submodularity is actually like convexity. And he says, like, no, you have duality results, you have optimization results. It's actually like convexity. So this brings up the question is like, is it more like convexity or is it more like concavity? And the truth is it's a little bit of both. So there is some evidence that it's actually kind of like convexity. So we'll see some of the examples in optimization. So you can do optimization. You have actually convex functions you can get out of a submodular function that are convex if and only if the function is submodular. And then you have concavity analogy. So you think about the diminishing returns properties. And there's one more thing. There's one way you can actually define a set function. So you can define a set function. One of the simplest set functions you can define is take the cardinality. Just count the number of items. That's not a super interesting function. It's a set function. It assigns a value to every set. We can make this a bit more interesting by saying, well, we take some scalar function, a function of the cardinality. So now we have a more interesting family of set functions. The question is, when is this a submodular function? So now that depends on G. If G is identity, this is a submodular function, which is the sum of the items. When is this submodular? And if you think about the diminishing returns, and if you work it out, what happens is this thing is submodular if and only if G is concave. So basically you can get submodular functions out of concave functions, but also you can get convex functions out of submodular functions. So there's different interesting relations. Okay, so now so much for sort of the setup of introduction of what is a submodular function. Let's look at some other things we can do with them. What about optimizing submodular functions? I talked a lot about, yeah, this is great, you can do it, so how do you actually do it? And I want to talk about two different types of optimization problems. One is how to maximize a submodular function. Think about maximizing utility, maximizing spread of information, maximizing the information of the items that you pick, things like that. Maximizing diversity, so recommendation, summarization, inference maximization, all of these problems would be submodular maximization. And then we'll talk also about minimization. So now thinking about convexity and concavity, intuitively what we are going to do is, it's easy to maximize a concave function, it's hard to minimize. It's easy to minimize a convex function, but it's hard to maximize it. Hence, if we talk about maximization, we'll use the concave properties of submodularity. If we talk about minimization, we're going to use the convex property. So we're going to use both depending on what's useful for us. Okay, so one more thing, if we think about maximization, will be the notion of monotonicity. What does monotonicity mean? It essentially means increasing function. So in a set function case, it means that as my set grows, my function can only increase. It can never decrease. So this happens for sure for coverage functions. The more items I add, the more disks I add, my area is never going to decrease. I'm always going to cover more. Maybe I'm going to get 0 increase in my area, but it's not going to be negative. But if you think about, say, the graph cut function, if you take a small set, here you're cutting 3 edges. Taking a larger set, you're cutting 5 edges, and you make the set even larger, essentially you're going to go back to 0. So on the right-hand side, this guy is not monotone increasing. The larger my set, eventually it's going to go down to 0. This guy is monotone. And for optimization, this makes it different. And I'll show you why. So for the moment, let's assume we are actually working with increasing functions, like information, like coverage. And so here's formally our optimization problem. We want to find a subset that maximizes the function subject to the constraint that we don't pick more than k. So why did I put this constraint here? If you think about a monotone increasing function, what's the optimal solution without constraint? Everything, great. So it's very easy, but it's not very interesting. So we'll put the constraint. So as it is, however, this problem is NP-hard, which means we cannot hope for an algorithm that runs in polynomial time in the size of our set, or of our ground set, to find the optimal solution. Think about problems like actually max cover, min cover, etc. These are all NP-hard problems, and hence this is hard. However, so let's try to shoot for the next best thing. Obviously, enumeration is bad. Optimal solution we cannot find, so let's try to find sort of the best possible approximation. So what is the next easiest thing after sort of enumerating all sets? It's essentially, one of these is a greedy algorithm. So what is a greedy algorithm? Essentially, you start out with the empty set, and then you find the item that's the best item just by itself. So this is easy to find. You just look at all the possible items, you look at their values by itself and pick the best. So here in the summarization example, it would be sort of look at which one covers the most other images, and that's the one you pick it and you keep it. And then you go on. You find the guy that's the best augmentation to your set. So which one gives you the maximum increase of your function if you add it to your current set? So number 2, if you have, say, these two for choice, this guy in the middle, it covers pretty much what you have covered already, so it's going to give you very little increase in your function value. But the guy on the right actually is pretty good, so you're going to pick. And so on. And so you go on, you pick one by one. Every iteration, you're going to increase the size of your set by 1 until you have reached k, and that's when you. It's pretty easy to implement. It's sort of a very straightforward solution. The question is, does it work? So here's an example how it works. Here, this is a sensing problem, so it's the same kind of sensor selection problem, and I'm comparing optimal, sort of the optimal selection of 1 item, 2 items, 3 items, etc., to what the greedy algorithm gives me. And obviously, optimal may be hard, but you see that greedy is actually pretty close to it. So you don't actually lose a lot by running this greedy algorithm versus in just an enumeration. So it looks pretty good. It looks like it's actually working quite well. But then the question is that a coincidence or does it always work? This is one specific problem, it's one example, does it always work? And so it does this hold throughout, and here's the answer. The answer is a theorem, and it says that if my cost function is submodular and increasing, and also non-negative, then this greedy algorithm is guaranteed to give me what's called a constant factor approximation. That means if I run this greedy algorithm, I'm going to get at least 63% of the optimal value, or 1 minus 1 over e times the optimal value. It can be better, so this is better than 63%. This is more like 95 or so, but at least that much. That's guaranteed. So that's pretty cool. So basically, if I know my function is submodular, I can run it. I'm gonna get a pretty good solution, and often in practice, it's much better than that. So why is this actually amazing? Is this natural that this is going to work? And sort of to illustrate that point, let me show you another example of a step function and subset selection problem. So here's a puzzle. This is your ground set of items, and your utility function is the following. If you pick any subset of these puzzle pieces, it's going to gain utility 0 unless you find the single set of items that actually fits into a puzzle. And then you get 100. Every other subset is going to give you 0. So now what happens if you run the greedy algorithm on this? Picking the first item, every single piece by itself has the same value 0. So you basically have no clue which one is better than the other one, so you're going to pick essentially a random one. What about the second one, the augmentation? Any 2 pieces are the same. They all have gain 0. So again, it's pretty much invisible to you which ones are the ones that may even lead to a good solution. So again, this is pretty much impossible. So at the end of the day, you're going to, like this I think has 25, so you're going to pick like 25 random pieces. And it's very unlikely that if you pick a subset of 25, a random subset, you're going to hit exactly this one. It's pretty much, so in this case, you cannot guarantee at all that your greedy algorithm is going to return anything useful at all. But what's different in this one from the previous case? So if you think about this one, there's no diminishing returns. So in fact, if you look at the marginal gains, they're going to be 0 unless you complete the puzzle. And in this case, they're 100. So they are 0 throughout, and if you get lucky, it's 101. But there's no diminishing returns. In fact, there's increasing returns. So this thing does not have the submodularity property, and here also the greedy algorithm does not work. So to sort of give you a bit more illustration, why does the greedy algorithm work? So we see it doesn't always work. It's guaranteed to work with submodularity. Here it's not. So why does it work with submodularity? So here's essentially how you prove it in a picture. So what happens as you select, let's say this is the utility value in the ith iteration of your greedy algorithm. And this is the number of items the greedy algorithm has picked. So it's 1, 2, let's say you go up. So what does this curve look like? You pick the best one. So in the first item you pick, you get actually the highest increase. Second item, because you've already picked the best one, and because you have diminishing returns, the second item's gain or return is going to be smaller here than here. So you're going to get something that looks like concave dimension. So this is sort of, it's going to look like some kind of concave curve. So, but how do we prove that this is a good value that you get? And that actually relies exactly on the fact that you're picking the best one and that you have marginal diminishing returns. So if you think about if this is the optimal value that you can pick with 4, essentially what happens is that if you look at this gap here between what's the gap to optimality, in each iteration, you're going to decrease that gap by a factor of 1 over k. So this guy here is going to be 1 minus 1 over k times the initial gap. And then from here to here, you again reduce this by a factor of 1 over k. And this just happens because in every time you pick the best item. So this is essentially how you prove, and then you just put these pieces together and you use that 1 minus 1 over k to the k goes to 1 over e as k goes to infinity, and this is essentially your 1 minus 1 over e that comes out. That's a bit of calculation. So this is the idea why greedy works, basically because you can guarantee that in each iteration you are closing this gap by at least a certain factor. So now if you look at your puzzle function, this same thing would actually look like this. So if you get lucky and you actually find the puzzle, you have 0 gain, 0 function value until you hit it, and then once you have 100, and then if you pick more, you go down. So this thing looks nothing like this concave guy over here. And this is essentially the problem, that all the information is hidden until you have found the optimal guy, versus here the information is not hidden. Sort of if you pick good items along the way, the value of a single item already tells you something about the value of this item in context of others. In the puzzle, the value of a single item tells you nothing about the value of this item in the puzzle as a whole. So that's the difference. That's the sort of intuition why greedy works for submodularity, but doesn't work for other types of functions in general. Just summarize what I said. Greedy works for 2 reasons. One is the submodularity, which tells you local information, like the value of a single item, tells you something about the value of this item more globally. And the second is monotonicity. So this is something that I didn't actually mention, but the thing is, adding more items can never harm you in this case, because your function value can never go down. Adding more items can just not increase your function value, but it's not going to go make it decrease. And in fact, this kind of global information from local one is something that you also use in convex optimization. That fact, gradient gives you local information, and that actually tells you where to go, what's a good direction. So this is actually sort of an analogy, and that makes it fact. Okay, so we know for monotone submodular functions, this is the argument. We have the simple greedy algorithm, and it's guaranteed to work. And this is in fact the best you can do in polynomials. But of course, not all of our problems are these kinds of exactly take k out of n monotone optimization problems. Maybe we have something more complex. Maybe we have more complex constraints. Or maybe we actually have a function that doesn't satisfy this monotonicity constraint. Or maybe there's another problem with this greedy algorithm, that is, what if my set of items is very, very large? Greedy algorithm is super simple, but if you have a very, very large data set, in each iteration, if you think about it, you have to scan through all your data points. You have to do this k times. So that actually can become expensive. So how can we deal with that? Is there some way to do this more efficiently than just the brute force? Okay, so let's look at sort of some of the other options that can occur. And essentially, the answer to all of this is variance of greedy. So the greedy idea actually holds more globally here. It's just that this exact greedy method that I described to you doesn't work in all of these settings, but essentially variants thereof. So I just call them greedy plus plus. So let me just show you one example what a variant of this greedy algorithm could look like. So let's say your constraint is not only to pick a limited number k, but let's say each of the items that you pick has a cost. Let's say they are sensors, and placing them in different locations has different costs. And you have a total budget. So you don't want to go over your budget, but you want to maximize subject to the budget. How do you do it? And essentially, you do something very similar. The first thing you can do is run greedy as a diff, basically until you have run out of budget. The second thing is you run greedy, but instead of picking the one that maximizes your gain, you pick the one that gives you sort of the best bang for the buck. Essentially, you scale your marginal gain of that certain item by its cost. And then you run greedy with this by selecting according to this function instead of without the cost. So now you get two solutions, and you take the better of them. That's it. So this is, you can see it's a variant of greedy. It's almost the same. And it still gives you a constant approximation factor. It's a bit worse than the 1 minus 1 over e, but it's still reasonable. And you can, in this particular case, you can do a little bit better with more sophisticated, more expensive versions of greedy by running it a few more times, more by doing what's called filtering. But essentially, you always have this greedy idea lurking somewhere in there. So always use diminishing marginal returns or discrete concavity. And then there's also another idea. So if these kinds of greedy variations don't always work, or you haven't derived them yet, there's another thing that people have done. And that is essentially go from discrete to continuous. I'm just going to show you sort of the main idea of this. If you think about the set function is actually nothing else than a function that works on integer vectors. So if you think about subsets, I could have a ground set of, say, 4 items, A, B, C, D. I take a subset of these items A and B. I can equivalently write the subset as an indicator vector where I put 1s wherever I pick the guys and 0s where not. So this is an indicator vector, and these are exactly equivalent. Any subset I can write as an indicator vector. And the important thing here is that every coordinate corresponds to an item. So if the coordinate is 0, I don't pick it. If it's 1, I pick it. Pretty simple. So now I could equivalently write my set function optimization problem as an optimization over binary vectors. And I can easily map from one to the other. Right? So this is essentially what this relies on. It says that, okay, I have a function that acts on binary vectors, and I do something to make this a function that acts on real vectors, where I don't always have to put 0s and 1s. I can put arbitrary vectors in here of 4 dimensions. So the dimensions still matter. Each dimension corresponds to an item that always holds here, but the vectors can be different. So now what I want is I want an interpolation of my function that works on arbitrary vectors, and if I happen to put an integer vector in there, it's going to have the same value. That's the idea. And then we solve a continuous optimization problem. Continuous optimization is possibly easier than discrete. So let's reduce it to a continuous optimization problem. That's the idea. So we have some constraints. Okay. So I made my set function, which is essentially just defined on these dots. These are all the integer vectors. I make it into a continuous function. And I'm going to optimize this guy instead of that. And then all I have to do is I have to go. So now I find a solution over here, which is possibly a fractional vector. It doesn't, most likely it's not going to be an integer vector, the solution that I find. So I have to go from this continuous space back to my discrete space and somehow find an integer vector that's a good approximation to my continuous vector. That's the idea. So I may have constraints. And the constraints just become sort of the convex Hull. So this is the continuous optimization problem. As you see, the function that I drew here is actually not convex or concave. It looks like a saddle point. But nevertheless, you can actually optimize this guy approximately by using enough concave direction. So now, where does the greedy idea come in here? And essentially, this thing has also been called a continuous greedy algorithm. So what is a continuous greedy algorithm? If you think about a continuous function, you greedily go in the direction that's sort of the best upward direction. That's like a gradient method. Think about gradient descent. It goes like you're trying to minimize. Here you're trying to maximize your gradient ascent. You go in the direction that's sort of along your gradient. And that's essentially gradient descent you can think of as sort of a continuous version of a greedy method. So this is what we're doing here. In this particular case, it's using what's called a Frank-Wolf algorithm. but it's essentially the idea of using your gradient information variable. So this is step 1, and step 2 is when you round. So again, it's essentially a variant of a greedy idea. Yeah. And this is also non-concave and non-convex. Surprisingly, this still works, and you can get good approximation factors out of it. Okay, so let me summarize the first part of this question. What do we do if we have other constraints? In many cases, variants of the greedy idea still work. So that's nice. And essentially, one sort of way to think about it is they work if your constraints are of the form that if a set is allowed, any subset of it is also allowed. So if you think of select maximum k items, selecting k minus 1 is also okay. Or your budget, you don't want to exceed your budget. Anything that's a smaller size subset of what you have selected is also feasible. So anything that, these are called down monotone constraint, any of these work. And the reason is that if you think about the greedy algorithm, it starts at the empty set and then it goes up. So if you exclude the empty set or anything else, your greedy idea doesn't really work anymore. That's essentially the high-level idea. So the second question is, what about if I lose the monotonicity of my function? So now I have a function that's submodular, but it can decrease as I add more items. What happens? So what happens if I run greedy algorithm on this thing? Here's an example. So here I just took my coverage function again, and what I did is I subtracted the cost of my items. Say every sensor has a cost, and I say my total utility is the area that I covered minus the cost, because I also don't want to spend too much. So I want to trade off these. So now you can think about it. It can happen that I've already sort of covered all the area, but I'm adding more stuff to it, so mostly I'm just paying more without any use. So my actual utility will go down. So here's a simple example. I have 4 sensors to choose from. Each of these has a coverage value. So this guy covers everything. It's pretty expensive. So minus 6 means it costs 60. So the utility of this guy by itself is 100 minus 60. This is how to read this. The other 4 are smaller in coverage, but also smaller. So now, without any constraints, I want to find the subset of sensors that give me the maximum utility. Anyone see what is the optimal solution to this problem? Yes? 2, 3, 4. Yes. So what we'll get is we'll cover everything, but cost is just 4, so it's pretty good. Okay, so what will our greedy method do? Greedy method will look at the gain of each of these guys and pick the one with the largest gain by itself, which is this one. 40 is better than any of the other green numbers. And at this point, you will see that if you add anything else to it, because you've already covered everything, you won't gain anything in coverage, but you will lose in cost. You'll pay extra. So at this point, the best thing is to stop. So your greedy solution will be just this. Versus the optimal solution is actually that. So now, and I can sort of make this example arbitrarily bad. So I can sort of tweak these numbers to make the gap between the greedy solution and the optimal solution arbitrarily large. So you see that in that case, actually, the greedy algorithm by itself is actually not such a good idea. But again, what you can do in this case is essentially the idea to do this optimally is you do a greedy from 2 directions. You add and remove at the same time. So you essentially do greedy from a full set and the empty set, and you see from both directions, and that works. So there's something called the double greedy algorithm, and that actually solves the problem that this thing doesn't happen anymore. Or again, running greedy multiple times. You run greedy once, and then you run it on sort of the stuff that's remaining, and one of the solutions is going to be. So that's the idea. So still, greedy versions work, but not exactly the greedy algorithm that we talked about it. So the last question is, what about scaling up the greedy algorithm? So since you actually, this thing works pretty well in practice, you may want to scale it to larger data sets. What do you do? And again, there's a few different things that people have done. I'm just going to show you one of them, and I had some references at my first slide, and there you can find some other work on like how to scale up greedy. So one simple idea you can do is you can distribute it. So take your items, distribute them across different machines. it's a very simple idea. Now you run the greedy algorithm on each machine. So if you want to select K, each machine selects K. And then you take these items and you put them together. Now you have whatever. If you have M machines, you have M times K, and then you select again. So the question again is this any good? And the answer is, in the worst case, not, but in general, yes. So essentially what you need is that your items are randomly distributed across the machine, and then you can prove that in general this is a good idea too. So in general this is actually going to give you like a half of what you would get with a greedy algorithm if you run it. And then there's other versions of greedy where you can do it in streaming, or they can just like, instead of selecting from the entire set, you select from a smaller random subset and so on. So you can do stochastic versions of greedy. All of these scale very well, and you don't actually lose very much in fact. So this thing works in general. Okay, so this is some of the more recent work you can actually do. Okay, so I've talked a lot about maximization now, and maximization you can think of discrete concavity, meaning some sort of discrete greedy version, discrete gradient ascent, essentially greedy algorithm. So what about minimization? Turns out for minimization, greedy algorithm is not at all a good idea. Think about finding a minimum cut in a graph and try it out, try to run a greedy algorithm on it. It's most likely not going to work very well. So what do we do? Oh yeah, where does it come at? Essentially in graph cut problems, and essentially instead of maximizing diversity and coverage, here we want to minimize diversity and coverage, meaning we want to find subsets that are somehow coherent. So you want to do this if you want to do clustering, if you want to find graph cuts, yeah, for image segmentation, if you want these coherent subsets, say of the gene data subset selection, of coordinate selection, things like that, structured parts. So the idea that we'll follow here is a difference. So while before we were mostly like discrete and greedy, here we will actually use the convexity connection. And the idea that we'll follow here is directly use what's called a relaxation. So we have our discrete function again. So these are all the binary vectors. And we want to convert our discrete optimization problem to a continuous optimization problem. So we want to find a little function f that works on all vectors with entries between 0 and 1, fractional vectors, that we can optimize that. So now the other function, I showed you the same idea for maximization, but the function I used for maximization, we used concavity. That's actually not a good function for minimization. We'll need a different interpolation. How do we find this? We want this interpolation, and it should have good optimization properties, meaning being easy to minimize. Otherwise, there's no gain. How could we do this? We have this f. We want to find some interpolation. How could we find a function that we can evaluate on fractional vectors? And here's one way you can do this. Essentially use expectations. So let me just illustrate this as an example. So here's my vector. It has some fractional entries. And again, each coordinate corresponds to an item. Think of the indicator vectors. Every coordinate corresponds to an item. So item 1 has value 0.5. Item 2 has value 1.0. So now I will look at this vector as a histogram. So between 0 and the max value, whichever is the max value you allow. And then I'm going to sample a threshold uniformly at random between 0 and whichever is the max value I'm allowing. So now this threshold cuts somewhere through my histogram. So some of the values are going to be above the threshold and some below. So I'm going to select all the items that are above the threshold, and I'm going to discard the ones that are below the threshold. So here I'm going to select 1, 2, 3 and discard the second. So this gives me now a discrete set. So now this is the S theta up here. And now I can evaluate my set function on that set, because now I have a set and I know what I do with it. And what I'll do is I'll just take the expectation over all possible theta for that set function. So this is essentially what this is. So now if you think about it, what does this actually mean? Essentially it means that what's the probability of taking everyone? That's just that part here. It's the minimum entry in my vector is the 0.2 is like the value that Between 0 and 0.2, if my threshold falls between 0 and 0.2, I'm going to pick everyone. If my threshold falls between 0.2 and 0.5, I'm going to pick the top 3. And if my threshold falls between 0.5 and 1, I'm just going to pick this one. And if it's above 1, then I'm going to pick 4. That's the idea. So essentially here I can only sample 3 possible sets. They are correlated, and this is now the expectation that I have. So essentially you can just compute it by knowing the order of your entries in this vector. So you can essentially compute it by ordering your entries. It's very easy. So this is something we can compute. It isn't per se obvious why we should use something like this. Why is it a good idea? It looks pretty arbitrary. Let me show you what this actually looks like. So here's a 2-dimensional example. So 2 dimensions means 2 possible items to choose from. And here's my interpolation. This is what it looks like. So what does it like? Do you see anything? What properties does it think? If you look at it. Convex, right? It's piecewise linear and convex. Non-smooth, it's convex. And this is in fact something that this property that this function always has. So this convexity is not a random thing that happened by the particular example I chose. It's actually something that happens always. This function always is convex. And this is the good thing because we want to minimize it essentially. So it's good to minimize a convex function. The second thing is that this is something that's specific to submodularity. The definition that I gave with this expectation is something, yeah, this is wrong. This is I'll forget about that. So this expectation that I defined over there, you can do it with any set function. There's no way I use submodularity there. You can just pick your threshold. You can evaluate your function at it. You can do it with any set. But this function is going to be submodular if and this function is going to be convex if and only if that set function is submodular. So this is something to prove. And now we are in a good shape. Now we have a function that's convex, that's an interpolation of our set function. Now we can minimize this convex function. And another way to see that this is convex is that you can actually write this function in a different way as a pointwise maximum of linear functions. And I think in the convex lecture you saw that a pointwise maximum of convex functions is always convex. And the pointwise maximum of linear functions is also always convex. So this is a convex function. I want to tell you a little bit what this is. So now we have a convex function. Let me just show you 2 examples of the Lovász extension. This is called the Lovász extension because Lovász defined it. What this Lovász extension actually looks like for some examples. So the first one is this following function. It is submodular. It's a kind of boring function. It's 1 if you have a set that's not the empty set, and it's 0 at the end. So it's kind of a not super interesting function, but let's look at what is this extension for this particular. So essentially, if you think about your expectation, whenever this threshold is such that you pick at least one item, it's 1, and otherwise 0. So in your expectation, you only have to distinguish between 2 cases. What's the probability of selecting anything at all versus none? And the probability of selecting anything at all is essentially the largest bar in this, which is the largest entry in your vector. So what this thing is going to do is it's always going to pick out the largest entry in your vector. So this is just the maximum norm. Second example I have is a cut function on 2 nodes to make it easier. So in this case, the function is 1 if we pick one of the nodes because we cut the edge, and it's 0 otherwise. So what do I have to be careful here? I take my expectation essentially. Now I have only 2, so think about just the 2 up here. When do I pick only 1? And with that threshold picking, there's essentially only one way I can pick 1, and that is if my threshold is somewhere between 0.5 and 1. Otherwise, I'm going to be. So when does that happen? Essentially, if my threshold falls between 0.5 and 1. So what's the probability of falling between 0.5 and 1? It's basically the difference between the larger and the smaller value, because I have only. So in that case, my Lovász extension is just the absolute difference between the entry at U and the entry at V. And if you do this for the entire graph, this is also called the total variation norm. So it's just the absolute value of the differences of your entries whenever you have an edge. So you actually get out some interesting known functions from this Lovász extension just by looking at your combinatorial functions and converting them to these convex. So second, let me say a few words about what is this BF here. So I said, oh, this is sort of the pointwise maximum of some linear functions. What are these linear functions? And essentially, this BF, it's what's called a polytope. The polytope is a convex set that's defined by linear inequality. So this thing over here, this red thing, is a polytope. So what is this specific polytope that shows up here? And essentially, this polytope is what makes all of submodular minimization work and polynomial time. That's essentially the tractability of this thing is underlying all of these results at the end of the day. So what is this BF? And it looks a bit complex, but it's basically all the vectors y that are dominated by your set. So what does it mean for a vector to be dominated by a set? Again, remember that every coordinate in our vectors, whenever we had vectors here, corresponds to an item in my set. So what I'll do is for all possible subsets, I'll sum up the values of my vector in that set. And this shouldn't be larger than f of s. And then the entire vector should sum up to f of s. This is my linear inequality. So this is the linear inequality just summing up. And it looks a bit complex. It has a few interesting properties, and I'm going to show you some examples of these. One thing is it's actually defined by an exponential number of inequalities. You see there's an exponential number of subsets. You remember the 2 to the 100. And nevertheless, it's actually possible to do linear optimization over this polytope. So essentially solve this problem in polynomial time. I already gave you the solution of this problem. If x is sort of the cost function, y is the thing you're optimizing, then the optimal solution of this linear optimization problem is the same as the thing up here. So it has a closed form solution essentially. So it's very amazing, and essentially you can solve linear optimization over this polytope by just sorting. That's all you have to do, so n log n pi. It looks a bit funky here, so this is what it looks like in 3 dimensions. Let me just show you 2 interesting examples of these so-called base polytopes. The first one is, again, our function of being 1 everywhere and otherwise 0. So the base polytope of this function happens to be the probability syntax. So all vectors that are non-negative and they sum up to 1. So again, we get out actually an item that we solve. The second example is something that you probably don't know, but I just kind of find it an interesting example. And this is what's called the permutahedron. So this is actually useful if you work with permutations and want to do optimization over permutations or so. And this is the following object. In 4 dimensions, think about the vector 1, 2, 3, 4. So first entry is 1, second entry is 2, third entry is 3, and fourth entry is 4. And then you take all permutations of these entries. So you have vector 1, 2, 3, 4, 1, 2, 4, 3, etc., etc. And you take all these vectors and you make them the corners of a polytope. So this polytope has all these permutations of 1, 2, 3, 4 as its corner point. That gives you a polytope. It's the convex hull of these vectors, and this is called the permutahedron. And it has the same interesting properties, and it's actually coming from a submodular function. So that's just a curiosity. It's useful in combinatorics and optimization over permutations. So that was, yes? The entries, so basically I'm defining a polytope by taking, so I can define a polytope by selecting vectors that are the corners of this polytope, right? So basically I take points in 2D, I would take some points, say this one, or this one, and then I just connect them. I take what's called the convex hull of these, I get a polytope. So now the corners of this thing here, this looks much more complex than this one, is essentially I take the vector 1, 2, 3, 4, and then I basically take vectors that are all permutations of this. So if this is my vector, then I take 1, 2, 4, 3, all possible permutations. So I have like 2 to the 4 factorial different permutations. And these are the corner points of a polytope. So I just make these the corners of a polytope. That's just, it's a bit of a funky definition, but I just take all permutations, and now every corner is a permutation of the numbers 1. And I can do it with arbitrary dimensions. Yes, exactly. This is 4D, so each of these is a point in 4D space, and I take the convex hull. Okay, so this was just some interesting distractions. Let's go back to optimization.
Question.
Yes? Yes? This one?
Yeah. The formula defining f does essentially support function of
yes.
the polytope.
Yes.
Does this give an effective way of generating? So basically, the dual norm corresponding to the norm as something if S had like being absorbing from magic stuff, I guess.
Yep. Yep.
So effective way of generating like norms
yes.
by specifying
yes. Yeah, that's a very, very good question. You're right. This is actually what's called a support function, and it is defined by a norm. So the norm that corresponds to this support function is that you take. It's coming from your Lovász extension. So the norm that's coming from this thing is that you take the Lovász extension. So I'll write this as maybe F. So you take the Lovász extension of the element-wise absolute value of your entries, and this is actually a norm. So this is a norm, and the dual norm polytope will be the base polytope. So you can actually make this analogy, and this has, you can use this for these structured sparsity problems, because this norm is going to sort of favor the sets that have small function values of the set function. So if you have a set function that sort of defines your preferences of, say, coordinate selections, you can use this norm as sort of a convexification of that function, and you can use it in optimization as a regularizer. So there's a paper by Francis Bach in 2010 that does exactly that, that discusses. But it's a very good observation. This is, yeah, this is the support function. Okay. Any other questions? Then let's go back to optimization. So what we wanted to do was we wanted to find the minimum of this submodular function. And then we said, okay, that's kind of hard. Let's find an interpolation of this function, which is actually also convex. And this is the Lovász extension. So we transformed our optimization problem from being over integer vectors or subsets to being now over all vectors that have entries between 0 and 1, which is easier to test. And now we have a convex optimization problem. And now there's all sorts of convex optimization methods that you could use to optimize this problem. The reason you can actually compute some subgradients, which is a friend of gradients, is that this polytope is tractable that I just. So now what do? Now we have a fractional value. What we still need to see is how do we get from this fractional value to a discrete value? Like how do we get back to our binary vector? Because most likely the optimal solution to this guy may or may not be discrete. So the rounding that you have to do in this case is actually extremely easy. So you look at your fractional vector. It has entries between 0 and 1. You pick all the items, all the coordinates that have entries larger than 0. You set them to 0 and you pick those, and the other ones, the zeros, you discard. So it's an extremely simple rounding procedure. And it is guaranteed to give you the optimal solution of the discrete optimization problem. So this is part 2. And that was essentially the result. This insight, these two things together with the ellipsoid algorithm, was actually the result that led to answer a long-standing open question, and that was, can you minimize a submodular function in polynomial time? And the answer was, yes, you can. You use this Lovász extension to apply convex optimization. So now, of course, there's many different ways you can possibly minimize this relaxation. You don't need to use the ellipsoid method. And these different ways to solve this convex optimization essentially lead to different submodular optimizations. So here's just sort of a chart that shows you some of the results. So you could use, of course, ellipsoid method. You could use what's called a subgradient method. You could use other methods as well, and you'll get different running times. There's also a way to do it in a combinatorial way, but even the combinatorial algorithms, which are related to max flow algorithms, they actually rely on the same relaxation. They solve the dual of this problem, but they actually rely on the same. So now you see the running times are actually pretty expensive still. So it's still sort of, people are still trying to get them down. So this is the latest result from 2 years ago. It uses the convex relaxation with some ideas from the combinatorial method. Then there's another set of optimization methods that rely on a slightly different relaxation. So essentially what they do is they also use the Lovász extension. You add to the Lovász extension the squared norm. And then you remove the constraint and you have to be between 0 and 1. So this thing is a bit more strongly convex. So it's a bit better behaved in practice in optimization. You can still do easy rounding, and this is what leads to what's called the minimum norm point algorithm. Essentially, they all rely on this Lovász extension in convex optimization. Okay, so this was what I wanted to say about submodularity and convexity. Essentially, it helps you to optimize. You get exactly a convex function out of every submodular function that lets you optimize. There's other applications of this. So someone already mentioned the norms that you can use for structured sparsity, variable selection. You can also use the convex properties to do parallel algorithms and decompositions, and even for variational inference in graphical models. So there's a lot of different implications that now these convex frameworks and the notion of subgradients and linearizations have that you get out. Okay, so we saw that actually optimization of submodular functions leads to very nice algorithms. On the one hand, you have this notion of discrete concavity, which gives you greedy algorithms. On the other hand, you have convex relations to convex functions that give you convex extensions. So both of these are kind of nice and they're implementable. One difference between minimization and maximization is that the addition of constraints. So I didn't see anything about minimization with constraints. And in fact, while for maximization, many constraints are still kind of easy, like pick only k, pick only in a certain budget. For maximization, as soon as you add constraints, the problem becomes much harder, like provably much harder. And the only thing you can do then is approximations. And the approximations kind of either are relaxations or you approximate the functions, and then it becomes somewhat similar to the 3D method. But I didn't want to talk much more about that because we don't have so much time. Let me just make a few comments about some other connections of submodular functions. So one is there's the problem of, can you learn a submodular function? And the answer is yes, you can. It's not easy, but you can. The main problem or challenge that you have to solve here is how do you represent this function? You know you want a submodular function, but now this function actually takes only a finite number of values. It's like just finite number of subsets, right? It's just exponential but finite, but you don't want to write it down. You don't want to write down all these values. So how do you parameterize your function? And that is essentially the main challenge of learning a submodular function. And there's been different ways to do it. The easiest way is to take a combination of basis functions. There's other ways of, say, approximating with decision trees or so, but that's essentially the main challenge. And in the list of references that I linked there, there's like some papers on that address. Then let me mention two more topics. One is that of getting probability distributions from set functions. So what is relations to actually probability distributions? And the second one is generalizing to more than binary vectors, going to integer or continuous vectors. So a little bit about probability distributions. And the main idea is you can get a probability distribution out of a set function by taking e to the f or e to the minus f function. And then you have to normalize. And so the difference is if you take e to the minus f, you're going to get large probabilities whenever f is small. So you sort of want to enforce coherence, something like that. If you take e to the f, you want to maximize diversity or so. You have like high probability means diverse means large function value. So here's an example. So here's what if you take minus f? So in that case, you satisfy the submodularity property actually to minus. You satisfy the inverse. with product. So the log of this function is minus the log of this function is submodular. The log of this function is what's called supermodular. It's the inverse of that. So you get this product. So what properties do these functions satisfy? And essentially, this log submodularity for probability distributions is very closely related to positive correlation. So essentially, if one item is 1, like I pick one item, it's more likely that I'm also picking other items. So they always positively correlated. One example of this is Ising models that are used, for example, for image segmentation or so. And essentially, the submodular function in there is a cut function. Whenever I have a labeling, so this is a distribution over binary vectors, or again, subsets, whenever I have two neighboring points that have different labels, I get a penalty, meaning probability goes down. So I want to basically select stuff that has a small bound, so coherent. Distributions that have this positive correlation and have log supermodularity are also called in statistics multivariate totally positive distributions, or MCP2, or positively associated or affiliated, and so on. So you may see these words somewhere. That is essentially what it is. What are the benefits of having this thing? Essentially, one thing is you can find the mode. Finding the mode is like minimizing that function in there, that set function. So we know now how to do it. What you can also do is you can approximate the marginals of this distribution, partition function, and so on, by also using some of the submodularity properties. So it gives you some computational benefits to actually know it has the submodularity. The other side is, what if we take e to the x? So in that case, the distribution has opposite properties. It's related to negative correlation. So first one was positive correlation, second one is negative correlation. So now negative correlation is a bit more complex than positive correlation. Essentially in the positive case, positive correlation pretty much equal to submodularity. Here, subset, like some special stronger condition than submodularity, relates to negative dependence. And negative dependence implies submodularity. So what's an example of this? An example of this is what's called volume sample. So if you actually want to subsample diverse sets, for example, you can describe each item with a vector, and the probability of picking two items together is proportional to the volume that's spanned by these vectors. But parallelepipeds you have. So the closer these vectors are, the smaller is the probability that you sample them together. And this generalizes to higher dimensions. So in a closed form, this is what is called also a determinantal point process, because you can write these volumes as determinants of submatrices of some big similarity or kernel matrix. So these satisfy very strong negative dependencies. And in theoretical computer science recently, these so-called strongly Rayleigh distributions have become popular for approximation algorithms, and they have this property that they have log submodularity and very strong negative dependencies. So what's the benefits of this? You get things like fastly converging Markov chain Monte Carlo and concentration inequalities. So since we're pretty much out of time, let me just show you one plot of the other generalization I wanted to briefly mention, and this is you can do submodularity more generally than just subsets and integer and binary vectors. You can essentially define a submodular function on vectors of integers instead of binary indicator vectors. And here's what it looks like. So you remember this f of s plus f of t is bigger than f of s union plus f of intersection. So essentially in the case of indicators, x and y are vectors, and the union becomes the element-wise coordinate-wise max, and the union becomes the coordinate-wise minimum. So this is what has to hold for. And you can do this for real vectors as well. So what functions satisfy this tendency? Is it convex functions? Is it concave functions? And the answer is some convex functions, some concave functions, and some functions that look like. So neither nor. So why is this potentially interesting? Well, the interesting thing is that many of the optimization results that I talked about actually generalize to this case. So now, even if your function is not convex, you may be able to approximately maximize it or to minimize the function by using essentially the techniques that I talked about. And that is the potentially interesting part of it, that you have a new class of functions you can actually optimize it. And what this actually corresponds to for differentiable function, this essentially corresponds to, if you look at the Hessian of your function, all the off diagonals are negative. Not really convex or concave, but something like directionally concave in some class. The other interesting thing is it's not equivalent to diminishing returns anymore. Diminishing returns is a stronger condition in this case if you have integers or continuous values. It means that your entire Hessian is pointwise. Essentially, each entry in your Hessian should not be positive. That's what this is. But similarly, like your optimization results, so this is better for maximization, having the diminishing. You get optimization results similar to the discrete case with simpler methods. Okay, I'm going to skip the application of this. You can look at it with the slides. And with that, let me just conclude. So we just talked about a lot of interesting details about submodular functions. So essentially, there's an interesting class of set functions that have relations to both convex and concave functions. Convexity you use for minimization, concavity for maximization. There's lots of examples of submodular functions that are relevant for machine learning in many different settings. And there's other relations to probability measures that have submodularity as log or super or submodularity there. And there's relations to non-convex optimization. So this is sort of the big picture of everything we talked about in this lecture. And with that, I just want to thanks.
Hello. Thanks for talking.
Yes.
I have two questions. One is related to formulation with the exponential of the submodular function, and that is how do you see stochastic algorithms like simulated in regard to this probability distribution that you obtain by the exponential of the submodular function? And then another question, then the second question that is related to that, how do you see other stochastic optimization algorithms like genetic algorithms?
Relate to this? Yeah, so about the simulated annealing, essentially you could optimize the submodular function with simulated annealing by doing exactly e to the f and sampling from that function. But then you have to sort of change your temperature. So essentially what you do in simulated annealing, right, you have sort of like, you use a scaled version. So it's something like that. So if beta is very large, then it's easy to sample from, and eventually beta becomes, no, the other way around. If beta is small, this is almost like uniform, and if beta becomes large, then you're essentially maximizing the function. So you could use this to maximize function essentially. What you need is that it's always easy to sample from this distribution. And essentially simulated annealing, it relies on how well can you sort of sample from it and how do you sort of adjust your beta. So it's known, like in the functions that I talked about, like these determinantal point processes, beta is 1. This is actually easy to sample from. As beta gets larger and larger and larger, eventually it becomes hard, because otherwise you could solve NP-hard optimization problems. So essentially, you could use this for optimization as well. In that case, you would sample, but eventually the sampling also becomes harder because that thing becomes more difficult. But yes, essentially, it's sort of the greedy algorithm would be doing sort of an extreme version of that, essentially. It's sort of a randomized greedy algorithm that you would do to sample from it, essentially. Yeah, so actually, if you look at some of the randomized greedy algorithm and this, it's not too far away. For genetic algorithms, so you can use genetic algorithms to optimize it. I don't know how it compares computationally to say the greedy methods or so. I haven't tried it. Can't say much about it. Maybe. Okay. Any other questions? Yes.
Hello.
what do you do if you have several agents who pick their element at the same time? If you have, for example, you're picking directions from a common starting point, then if I have 3 agents, the optimum solution is another one than if they pick their elements after each other. So you want the 3 agents are jointly optimizing the same function, or you want something that's sort of taking measurements? Okay. Yeah, so in that case, it's similar to the distributed optimization question. If you actually partition your set and each guy independently picks from each set, in the worst case, they are picking the same thing, right? So they're all running the same greedy algorithm and they're sort of all picking the same thing. So if they all had the same items, yes. So in that case, you probably want to randomize or do some communication, or you want to oversample, because that's essentially the worst case of this distributed algorithm that I talked about, that I like sort of brushed over. So that's also the reason why you want a random permutation of your items to distribute across the machine, that the probability that this happens is very unlikely. So in that case, it's fine. If you actually really select, like everyone has the same items and they select in parallel, you need to do some communication or some over-selection to counteract this, or some randomization or so. That's exactly the point that makes it not so easy to distribute greedy algorithms. It needs a bit of thought. Yes?
I wanted to ask a question about how to check whether a function is actually submodular, because we saw a few examples of submodular functions, as well as in some examples it seemed that the diminishing returns property is not sufficient to guarantee submodularity. Referred to, for example, the sensors example.
Oh, okay. So diminishing returns for set functions is always enough to guarantee submodularity. It's only not enough if you have these integer functions that I showed in the very end. So in general, if you have a function over binary vectors or subsets, diminishing returns is equivalent to submodularity, and that's typically the easiest way to prove submodularity. So you just look at sort of, okay, how does my marginal gain, how does it decrease or not? And often that's the easiest way to prove submodularity. The other way you could try to prove it is to start from a function that you know is submodular and show your function is actually a sum of such functions, or what's called a truncation or something like that, like some operation that preserves submodularity. Often the direct proof is the easiest.
We should know one more question for the lunch break.
Look, I was wondering if there's any notion of submodularity on finite subsets of continuous sets. So what might transfer to the situation?
So if you have a finite subset of a continuous set, oh, you mean that your actual ground set is infinite?
Yes.
And you pick a, yeah, so essentially it would be the same. So actually I showed this example of, say, these determinantal point processes, which is essentially subsets of some ground set, and then you have the probabilities. You can define the same thing also for infinite, like continuous sets. It's actually the you can do it. You have to be a bit careful. Okay, does your set, do your like size of the set goes to infinity? Is it all well defined? But in principle, yes. And of course, greedy algorithm is going to be a bit harder to run, etc. So you have to think what to do with it.
Okay, so I think we should probably move all other questions offline. So first of all, I would like to thank Stefanie again, and then afterwards I have 2 short announcements. So don't run away yet. But let's first do Stefanie.